Okay. Uh, I'm audible to you. Could you just let me know one more time, like whether I'm audible or not? Hello, hello, HOT Physics. Is that your name? Hello, hello, I'm audible. Hi, Panasa. I'm audible. Hello, hello, Panasa. Am I audible to you? Oh, okay, thanks. So, okay, we can start. So before beginning, if there is any questions or any kind of queries related to this course or anything in particular you are facing some issue, then you can just tell me right here. We can try to go through. Uh, so everything is fine. Like you're following this course. You can tell me like any problem, uh, any kind of issues with this course. Like everything is going fine. Well, right now only two of you are right here, so maybe anyone can, if you are having any real sort of issues, then we can try to clarify them. Okay, so maybe we can go through if you are not have any questions as of immediately right now. Maybe I can. Yeah, do you have anything,
Oh, hello,
Vanessa?
sir.
Yeah,
I just wanted to ask because I'm still struggling with the concept
uh,
of adjoint operator.
sorry, could you repeat it again?
I'm still struggling with the concept of adjoint operator.
Concept of adjoint operator.
Yes.
Yes. So, what happened? Like, is this with it? Yeah. Uh, what happened with adjoint operator? Sorry, I'm unable to hear you properly.
Oh, can I repeat, sir?
Yeah. Now fine. Yeah.
I'm still struggling with the adjoint operator.
Adjoint. You mean adjoint operator? Is there any question that you are unable to understand, or some concept? Like,
Okay, let me just go through the notes that I wrote.
uh, Sorry, I'm unable to understand. Could you say it again one more time?
Mm, can we come back to the question again, say later?
Okay, so you want to okay. So you want to like frame it properly, then you can
Yes, sir.
think and just tell me later. Fine.
Yes, sir.
Or else like you can use the chat box right here. I can also see that.
Okay, sir.
Okay. Okay. Okay, if not, if there is any more question like, from someone else, like any kind of doubts, questions, uh, any kind of clarifications you need, because it's been 2 weeks and uh, I mean this is our third week of problem solving session. So we have done like quite a few questions over these 2 weeks, and also you've been practicing problems which are already uploaded on your NPTEL portal. So there would be some questions, there will be some doubts. So if you are really unable to follow something, then you can just tell right here. We can try to sort out them. Okay, so if you, yeah, is there any question, Panas?
Oh, no, sir. No, sir.
Okay, okay. If not, then maybe we can go through, and meanwhile, if you are getting any questions or any sort of doubts, you can raise them like whenever you want. So in this 2 hour session, so okay, maybe we can begin our uh, today's session. So we will discuss again this linear algebra. So the topics that we will take this time, it would be linear independence, like this topic, like I mean, which we discussed last time also, and relevant questions also we have solved them. But there was few assignment questions related in your assignment too, which I have put them up right here to solve them, to discuss some of those, and then we'll begin with some uh, questions of new topics that I think I you have already gone through them. If not, then the lectures are already out there. So the new topics will be this time for this week's will be eigenvalues and eigenvectors, similarity transformations and diagonalizations, and unitarity and hermiticity. So, there have been are you guys following this lectures like regularly like on your NPTEL portal? Like, are you able to follow them now? Like I think till week 4 the lectures are uploaded. So like, like hello. So are you able to follow them? Like are you following those lectures? Okay, so Vanessa is saying he's following those lectures. Well, I hope others too like are also going through those lectures. So just like follow them regularly, because if you miss any lecture, then there will be a whole sort of a trail of things that you will miss along uh, in coming weeks. So it's better to follow them and also solve some relevant questions right there when you finish up your understanding your concepts. So okay, linear independence. So I have brought this thing back again just to clarify this a bit more, and also like go through some questions related to your assignment too. Uh, Linear independence, like as I said last time, like the same thing. Uh, I have I'm showing here right now as well. This suppose like if I have a basis, if I've chosen a basis like B, that is 1001, or like 11, or 1 minus 1. So this basis you can see like they form uh, I mean, they are, since they are linearly independent, so they form a very good basis, and from which we can span the entire vector space. So, so that is like one of the thing that you need to keep in your mind, like in order to have a proper basis, your vectors should be linearly independent. So, but if you choose a basis like of uh, this way, where b is equals to 1 0, and the second basis vector is 2 0. So this set you will see like this set is not linearly independent. In fact, I mean, they are linearly dependent. So you can see that like the second vector is a scalar multiple of the first vector. So this, uh, if I call this as V1, and if I call this as V2, I can say I can write V2 as 2 times of V1. So this is, since this vectors form, I mean, since these vectors are not linearly independent, so they won't form a basis which could span the entire vector space of R2. And similarly, like if you are in R3 vector space, you need to have three linearly independent vectors. So, and so if you are given any arbitrary dimension basis set, that is is equals to E1 till En, some n number of uh, basis vectors. And the way to check linear independence was like you needed to satisfy this condition where this alpha 1 E1 till alpha and En, the total sum going to 0, uh, uh, which implies that like this coefficients of this basis vectors, they individually goes to 0. So that was the the idea of linear independence. And suppose if any one coefficient is not 0, like you can say that like you can express the whole thing something like this. So or else let's say if I have only three basis vectors, and in three these three basis vectors basically like spans my R3 vector space. So uh, and for the basis vectors for this will be something E1, E2, E3. So and if you want to check whether they are linearly independent or not, since I'm calling it as basis vectors, like they form a basis set, so they would be linearly independent. But let's say if I assume I don't know whether they would form a basis or not, so you check this condition, and if they follow this this other condition, like that alpha 1 alpha 2 each and individual goes to 0, then they are linearly independent. So here also, like if I would check alpha 1 E1 plus alpha 2 E2 plus alpha 3 E3 uh, is 0, then it should imply that alpha 1 alpha 2 alpha 3 is individually goes to 0. But in any case, if you find that if you, any one of the coefficient is not equal to 0, then you can have such conditions like here. Then your linear independence will not be fulfilled among those vectors. So they would be linearly dependent. So likewise, we saw one question like we took these three vectors and tried to check the linear independence. So if you remember, like we find like that they were not actually forming uh, a linearly independent set of vectors. Like the one argument that we presented here is like we said it like they were forming a many non-trivial solutions. Instead of forming a unique solution, we found that that this system of equations doesn't have any I mean, they doesn't have any unique solution. So what I meant was like we after all we wanted to check this coefficients a1, a2, a3. So we found a3 individual going to zero, but a1 and a2 weren't. So uh, and we concluded that like from solving these three equations, so this forms a system of equations. And like if this system of equations uh, if you go on and solve, like you can easily get them. So what would be A3 and A1, A2. But I here today, like I'm like giving the same question, but like this time I wanted to uh, tell you that you can just simply guess them whether these vectors are linear independent or not just by looking at the I mean at the matrix form. So what would be the matrix form? So like if you have this kind of three different equation, like you can construct a matrix like whenever you have you are like checking this like condition, like you can always construct them in a matrix form. Like let's say um, here like for this same case I can uh, do this. uh, let's say I'm constructing a matrix of some let's say this is this is actually a column vector and if I call another matrix M, where I would just uh, give this numbers, or you can see like the coefficients of this a1, a2, a3 from this system of equations. That will be, you can construct one 3 by 3 M matrix. And then you just calculate the uh, um, determinant of this M matrix. So for this case, like if you would calculate the determinant of M matrix, like you will see that this will give you 1 times of 6, then minus 2, uh, minus 2, 3, then minus 1, 0. So this is actually giving you 0. So determinant of this M matrix, if it is giving you 0, then you can easily say that the vectors that you are taking, like this E1, this V1, V2, V3, which is given here, they are not linearly independent. One reason to think is that let's say if this M and if I call this A, this A is some sort of a column vector. If they form equation like this, and uh, so you want to know you want to calculate this A matrix, this A A A vector, because you want to know A1, A2, A3. So uh, and before calculating it, like one obvious thing that is coming to your mind would be like taking A to be 0, because that is that is trivial. So but we don't want that. Like we looking for something like of a non-trivial or a unique solution to it. So like a unique solution, there are techniques to see this problem as like if you see like the determinant, it would easily like give you the correct way to predict whether they are linearly independent or not. If it is non-zero, if this metric is non-zero, then then that would have been the case where a1, a2, a3 like would have been sorry, this v1, v2, v3 would have been linearly independent. So I think this is also like explained to you in your lectures, which is there on your I mean I think on your week 2, maybe that would be there in your week 2. So you can just check there, clarify. You can clarify there. So related to that, like there were a few questions in your like last assignment, and so maybe from here you can uh, get a more better understanding. So this was your assignment to problem 8. Uh, the question is like, let us consider the set of n distinct vectors. So the vectors are given as this. Uh, so the vectors are the ket 0, ket x1, ket x2, and till ket x n minus 1. So these are like Dirac notation. These are basically column vectors, which I was like showing you before. So which are all part of some vector space. The vector 0 is a null vector. Then which of the statements is true? So you have to figure out. So So the first statement says that this is necessarily dependent set of vectors. This is a necessarily independent set of vectors. This may be a dependent or independent set of depending on specific vectors chosen. So basically, like the statements from the statements, like you can just say that like these vectors like are basically forming a linearly independent set or dependent set. So um, so in this case, just you can just from the condition which I showed you right from the start, like this one, this condition from there itself, you can say whether like they can form a linearly independent or dependent set. So let's say the coefficients like they uh, let a1, a2, and till a and minus 1. So these are coefficients, these are numbers basically, they are in complex. So in general, you can always consider complex field. So then you can write them as linear combination of these vectors in the following way. So this is the condition we need to see. But here you can see already this uh, 0 is given to be a null vector. So from here you can say that like this a0 will be obviously going to 0. But in this case, it is not necessary that the coefficient that you have chosen a that that can individually go to 0, because even if it doesn't, this 0 is this null vector will already will make this term to go 0. So since this is a null vector, so this term will just go away. Like it is 0. It is already. So you need not to like have to be assured that like whether a will be individually going to 0 or not. So so that's why like you can write this again, this entire linear combination without this first term. Uh, or else like um, I mean like uh, you can just write this as this equals to 0, because this is null vector. So like here this 0 means like it is a some 0 vector, it is lying on the right hand side. So what I did with the null vector which was there on this side, I just brought it on the right. So you can see that like this entire thing, like and now it is becoming a it has become a sort of a some linear combination of vectors depends on uh, this final null vector. So now, like you can see, this the structure is giving an impression that this is a dependent set of vectors. So this so that's why, like you can say, this zero can be uh, expressed in terms of other vectors. Thus, this entire set um, forms a dependent or is a set of linearly dependent vectors. Linear. So, so from here you can see that the statement is the correct one among these four. So that is what like I was also like referring at the beginning, when I had this alpha 3, when I make this alpha 3 something non-zero, you can express the other vector. I mean this corresponding. I mean like when the coefficient of this third vector is was not zero, like I was able to express this third vector in terms of other. So that was the thing which happened then in this question also. So so this is another related problem. So this is again your assignment to problem 10. So here in this question, like here two vectors, I mean a set of basis vector is given, and uh, uh, yeah, uh, this is a basis vector for some vector space V, and then they are redefining some uh, new basis, new set of basis A and B, and you have to again check which statement is true. So here you can see this A set is given. Uh, yeah. So again, you have to check whether they are if in order to form a basis set, your vectors need to be uh, like I think someone had a question like Akanksha, I think you have a question. Hello, Akanksha. Akanksha, Razul, I think you have some doubt somewhere. Like I found your hand raised, so you can just simply tell your question if you have any doubt by just unmuting yourself. Okay. So yeah, I was telling if you have this basis set where your basis vectors are one of your basis vector is this one plus two, the state one plus state two, or these are basically column vectors, and the uh, other one is given as alpha 1. So you can see, like you can take a linear combination of these two uh, as, let's say, uh, C1. Yeah, for B basis vector, can similarly write a equation. You can see in both this form, like we can still able to write this linear combination. Like why we are writing this linear combination? Basically, we want to check that condition, like the one which we did before as well. So, like this is what we want to see to check the linear independence. And if they form a linear independence set among themselves, then they would definitely like span the vector space, and that would be your basis for the given vector space. So here in this first like in this set, like you can see that like if I could uh, see if I can make C1 and C2, or there if exists a C1 and C2 which can go to 0, then this entire equation will satisfy. So like the first vector which is given in sum of 1 and 2, so it doesn't really tells you something very new. It's just basically like I can just rewrite it as um, C1 plus alpha C2 plus C1 plus sorry, 0. So again, like if I uh, uh, have a condition that if I have a situation where C1 and C2 both goes to 0, then effectively the coefficient, each of the coefficients will also go away. Like if they goes to 0, then again we have this basis set to be linearly independent among themselves, and they would span. And the B like for set B, it is like quite straightforward. Like again, the same argument goes through. So so here the correct statement would be the first one. So are you able to like follow this? No? Hello. Someone had it up. Yeah, Panasin.
Oh, so I wanted to go to the one with the null vector, the previous question.
Oh, okay. Right.
I
Yeah.
wanted to ask because is it possible to say that you can actually compare the question to the number of equations versus the number of unknowns? Then in this equation, what happens is the number
Uh,
of unknowns becomes a1 up to an1. which is now n minus 1 unknowns,
Okay.
but the number of equations are n because of the dimensions of one of the vectors from the vector space. So we
Uh,
have
uh,
n equations versus n minus 1 unknowns. So there is a
uh,
discrepancy where the
mhm,
number of equations are much
mhm,
bigger than the number of unknowns. So therefore,
uh,
can we conclude from that statement that it is actually
mhm.
linearly dependent? Because
Uh, uh,
that's what I
uh,
did.
Yeah, yeah. Like you're like yeah, you're there. I think you are telling it right. Because in the previous case also, the last time around when we were discussing this question,
Yeah,
the
that's right.
same the yeah the same sort of thing happened there. Because like you would see like here like this system of equation didn't like gave any like unique solution because of this linearly dependence thing. So, the point here is like for linear independence, like basically you need to have like this all these coefficients like going to zero. So right now, like in this question which you were like having doubt. So here also you see like even if I say let's say like I don't know this a coefficient. I mean the coefficient to null vector. I but that coefficient is still there. So the thing is like uh, I haven't like, taken away this coefficient. Like the thing is like I'm expressing this null vector back again in terms of other vectors. So this null vector I'm expressing it in terms of other vectors. That is not the thing that I want if I really need a system or if I really need a linearly independent set of vectors. Because if I am able to express any one of the vector among that set in terms of others, then that would spoil all the linearly independent like the linear independent criteria can only be satisfied if individually all of these coefficients goes to zero. So here like I'm expressing this in terms of uh, other vectors, like the one which I started with my discussion as well. So here this E3, like you can think of like E3 like initially belong to this kind of uh, R3 vector space where I am able to span entire R3. But now, like if I say this alpha 3 is not equals to zero, then my situation could be of something of this where you can say that E3 vector basically I can express in terms of E1 and E2. So that is the case of linearly dependent situation. So the same thing happened here also. Here I have expressing this null vector in terms of this, but you are also right. Like the number of uh, if you form a system of equations like among coefficients and vectors, you would find like it won't yield a unique solution. So the one which we discussed last time also had the same problem. Yeah. So is that like all right? Like, are you able to like? I mean,
Yes, because that's actually how I answered the question, and I got the first, and then I said it's actually linearly dependent.
so the best way to do is like you just have to fulfill these two things, these two conditions. Like
Yes,
if you can fulfill these two conditions, like then you
yes.
are there with to say that like they would. I mean um, they would form a linear independent set.
Okay.
And the other one is there also like which I will come to right now. Like the one like to understand using system of equation, like using determinants. So like there is a question in your assignment like from where you can know like how you can just guess it from other way. Like but the main idea of linear independence actually. stems from this too.
Oh,
So, but if you have a like a let's say, I think it would be better if you can just go to that problem and see. You can get a understanding from a different perspective. So, uh,
thank you, sir.
yeah. So, like, we'll see this question. Uh, Yeah. So here this four set of vectors is given, and then it is asked like whether they form a three-dimensional vectors. I mean, they form a basis or not. So again, like to form a basis, we need to check this set should be linearly independent among themselves. Where I mean, each of these vectors should be linearly independent among themselves. So check that like we can uh, start like uh, maybe I can tell you like in this way like the one which I did earlier also like you have to construct matrices. So so the in set A you have this uh, V1 or let's say like I can just simply write one. So I've written this matrix like this. They are basically the coefficient matrix, like similar to one I like showed you right here, like this M matrix, which I constructed out of this system of equation. So here also I have a similar thing. And now like what you have to do, like you just have to like check the determinant of this matrix. So if you would check that, like you would find like the determinant would be, I think this will give you a zero determinant. Like, yeah, like you can check it once, like you will find that like this determinant for this A matrix will give you zero. Like for B matrix, like why I'm doing checking this determinant again, which I said you earlier. So they basically like form this kind of situation, or let's say AV is zero, where A is this vector and V is my EX, EY, EZ. So I'm basically writing AV is zero. That means I, yeah. Uh, so I want like this condition to be achieved, but here you will see uh, uh, if I can like have you like gone through the I mean this earlier lectures which was there like on your NPTEL portal like on ranks and dimensions of matrices. So, like, what I wanted to say here, like, when this determinant goes to zero, what happens? Like, your rank of this matrix will be less than the order of this matrix. So here, the order of this matrix is three by three. So, but when you check this determinant of this matrix, you are getting the determinant to be zero. So, if the determinant is zero, then you can say that the rank of that matrix will be less than this order, the less than three. It will be less than three, the rank will be. So, so in this case, what happens like your this vectors, which is like given here, they form. a, a linearly dependent set, because you will see that like you can express one of this vector in terms of others. So uh, like the same way, like you can check for others also. uh, like for B matrix, it is 1 minus 1 1 1 minus 1 minus 1 1. So like in this case, like you will see that like the determinant would be uh, it would be something, I think, uh, minus 4. Let me check. Yeah, this is minus 4. So so in this case, the determinant is non-zero. So if the determinant is non-zero, then they would form a set of linearly independent vectors, and they will form a basis. So the other way, which I think like Parnase was trying to know, is this like if you are given this kind of vectors, like something of some other any arbitrary combinations of vectors, then the best way to do is like just and you can check whether the determinant is uh, uh, zero or non-zero. So depending upon the non-zero or zero value of determinant, you can say whether your set of vectors are linearly independent or not. Just like the case which I showed you before also, like the problem that we discussed last time, like we found like they have this kind of uh, relations, which actually spoils the uh, uh, property of linearly independent vectors. So here also I showed you using this vectors. So last time we found that these were not forming a linear independent set. So now you can do that by checking this uh, determinant of this M matrix. So like this way also, like you can have an idea like how you can obtain a linear independent set. So maybe like Panase, like you clear, like if you have this kind of arbitrary situation, like you can check linear independence in this way.
Oh, yes, it was. I actually constructed the matrices and then I did the rank reduction,
Uh-huh.
echelon, row reduction, echelon form, all that stuff. And then you find the rank of the matrix. If the
Uh-huh.
rank of the matrix is 3, then the set is actually linearly independent set. If it
Yeah,
is
yeah.
not, if it is less than 3, then it is dependent.
Depend. Yeah,
So
exactly.
for A, I actually got dependent, but for B, C, and D, it's actually linearly independent sets.
Yeah, yeah. It is linear independence. I think for C and D also, yeah, they form linear independent.
Yeah, I think the determinant way is actually faster than the actually finding
Yeah,
the rank.
yeah. Just you can just straight away you can calculate the determinant, and from there you can just say like whether it is zero or non-zero. Based on it,
Mhm.
you can conclude that the given set of basis vectors are linearly dependent.
Yeah, so I think I'll actually do it that way.
Yeah, like this is a quicker way to say like whether they will be linearly independent or not. Yeah.
Okay.
Yeah. Okay, so if anyone has any more like doubts or questions, they can speak. Uh, like, everyone followed this up to this point, or any questions? If not, then like we can move on. So this is again your assignment problem. So this is assignment to problem 4. So here the question is like like for what value of lambda, like the system of equations like will satisfy. So again the metrics that I was like telling you just in previous problems, the same way you can do a matrix form calculation in this question for this question as well. So uh, like so you can construct a similar kind of coefficient matrix like this. Then so in order for this system of equation to exist, you need to I mean you for a unique set of solution for this system of equation, uh, you need to uh, check again the determinant, because if they if the determinant goes to zero, then that will tell you that uh, this system of equation, like it can have any it will not have any unique solution. For a unique solution, the system equation like needs to be non-zero. So but here in this case uh, if I take determinant, so again that is lambda minus 1. So just you have to take the determinant here, and you have to uh, set this determinant to 0. So you'll find if you simplify this, uh, you will get. So now the choice of lambda for which you can get a solution, or you can like uh, you can obtain a system of equation that would be uh, one would be like lambda 0, and the other you can compute from here, uh, which will give you lambda basically. uh, I think this is a quadratic equation which you people are familiar how to calculate it. Square, that is 9 minus 4ac, so that is 36, and then 9, that would be 33. So for solution of this system of equation, uh, uh, you have this this lambda values. So this is just a like a question that I think you have already seen before. I mean, before understanding matrices also, like this is like the way you calculate for solution of this kind of equations or system of equations. So I think this is straightforward. If you have any questions, you can ask.
Sir?
Yeah.
Oh, I wanted to actually point out that we can actually use the fact that the matrix M is a symmetric matrix.
This.
I mean,
Sorry.
matrix that
A,
you.
A A is a symmetric matrix. Yeah, it is symmetric matrix.
I think we can exploit that fact to
Uh,
make the calculation simpler.
like symmetric matrix. But actually, yeah, the thing is like this is symmetric metric, correct? But like, but we need the value of lambda. So for lambda, like it's just simply we set this determinant of this matrix to zero, and that
Okay.
can give us the value. But I don't think like being symmetric will also provide some more additional condition that could help us to give a solution. Mm.
Oh, okay, sir. No problem.
Because here just you have to take the determinant and just set it to zero.
Okay.
So, like it's straightforward. Like I guess you have seen or solved this kind of questions like
Yes, sir.
previously. Yeah. Okay. So maybe okay. If all of you are already like fine with this, if you have any questions, you can ask, or else like we can move on. So the correct options will be B, C, and D. So, here like your, uh, this week's topics like one of your like main topics of this week uh, course was like on this eigenvectors and eigenvalues. So so the one which I showed you right here, like it is this question is actually like related to this eigenvectors and eigenvalues. Like maybe I can tell you how it is. Just so like what is this eigenvectors? Like they basically they form a linear map on a vector uh, through a multiplication by a scalar. So that is like you have a operator or like in terms of mathematics that we do, like we have a matrix A. So we operate it on a vector, and that gives us is that gives that vector by scaling it with by some lambda. So lambda is some scalar, so which we call that is eigenvalues, and x is your uh, eigenvector. So like this eigenvectors, like you have to why you call them eigenvectors, like because you operate this operator, like there exists operator when you operate them uh, on that vector. That vector like again it yields back with a scalar multiple. So it is it is kind of a linear mapping that you're operating a vector A on a vector, and you are extracting a scalar out of it. where you see that like that matrix still or that vector, I mean that vector is still a linear one. I mean, like the vector is not like it has got a squared or something like here also, or maybe like let me just tell it here completely. So the way to see this is like this actually again a kind of a uh, uh, equation, a system of equation. It also appears here. So, like if I see this is the condition, like if A is some matrix and X is some column matrix and lambda is a scalar, so uh, then I can write this as I can bring this lambda X on LHS, where I can write in this way, where I is my some I is the identity matrix of order corresponding to the uh, A matrix. So here you see that this again will give you, or which is I have written. So this again will give you the situation of the form which you found earlier in this person. So this one. So if you can see, like if I would compare with this earlier one, like I can write this A matrix. I can the I can write this uh, A matrix to be something of uh, um, -1, 2, 1, and then 2, -1, -2, and 1, -2, -1. Then if I uh, and then if I take A minus lambda times I, and if I uh, multiply it with x, then that is basically 0, where x is x, y, z. So this x is basically your eigenvector. So that is the same thing like which I am trying to describe here. So this actually forms a system of equations again, and like here you saw like this entire thing they form a system of equations. So basically like the eigenvectors that we generally we are interested because they give us some non-trivial solutions for this for a particular given system of equations. So to solve this um, uh, system of equation, what we do, we take the characteristic equation. The characteristic equation is basically the determinant of this matrix. So the same thing. So here, like this m is basically this a minus lambda I. So if you take determinant and then you set it to 0, that will uh, uh, give you the equation where you can proceed to calculate the roots. So the roots will basically give you the the roots here is the basically the eigenvalues. So and that gives you a non-trivial solution for your system of equation. So using particular value of lambda, you can construct like a corresponding vector x1 and x2 and x3, where this would be your uh, eigenvectors, which are basically your non-trivial uh, uh, solutions for these equations. So like here, like which we calculate the lambda, we had like three different values. So this was not your solution actually. The lambda is 0 and these option C and D. So here also correspondingly to these three eigenvalues, you can calculate your uh, your eigenvectors. So mm, so like here the eigenvector was this x y z. So correspondingly to values of lambda 1, lambda 2, and lambda 3, you can construct x1, x2, and x3, which will be your eigenvectors, uh, where you will have different values of for x1 you will have some x1, y1, z1, and for x2 you will have something x2, y2, z2. So these are basically your eigenvectors. So I think in detail, like these things would have been taught to well by Professor Aditya Samal in your lectures. So so using this eigenvectors, we proceed further in understanding various other aspects of linear algebra. So one of the important thing is similarity transformation. Similarity transformation is uh, basically it is explained by this uh, this is your definition for similarity transformation. So what happens like in this transformation, you basically change your basis from one vector. You basically change your one basis to the other. So like and but the overall the inherent structure remains the same. By that I mean like this A and B will share some common properties. Like this A and B will have uh, same characteristic equation, same characteristic equation, same A and B, and then same eigenvalues and uh, yeah, and same rank also. So yeah, mm, but to know that if there exists such similarity transformation between A and B, you need to assure that there exists a matrix P, which is an invertible matrix. So which means its determinant is not equal to zero. So uh, yes, is there any question? Okay, so so using this similarity transformation, using the idea of similarity transformation, one of the like important applications that you see is constructing diagonal matrices, because diagonal matrices are of uh, are of greater interest, particularly when you go and study in your when you study physics in your in your upcoming courses or in your subsequent courses, you will find like in particularly courses like quantum mechanics and quantum theories, like you will see that like having a diagonal basis like actually solves a lot of problem. Like it actually gives you a very direct idea of having eigenvalues and eigenvectors. So what happens like in this using the same definition of diagonal basis, we do this diagonalization. So I have a matrix A, and I using this like this similarity transformation, I can make this A matrix to be a diagonal matrix. So as I was telling, so in this similarity transformation, we are going from one basis to the other. So initially we had some non-diagonal basis to some other diagonal basis. So like what happened, like let's say like as earlier I was telling you, I was taking some basis of this form. So, uh, so let's say this basis belongs to a particular, uh, it actually constructs a, I mean, particular matrix. But when you like do a symmetry transformation, you will see that like you can end up with a different set of basis vectors. where you will see that like when you will arrange this basis vectors in a matrix, you will find that they would form a diagonal matrix where only diagonal entries would remain and all others will be zero. So we'll see like some related problems to it, which you can like think better. Uh, so like mm, so one of this question is this uh, is related to like to these concepts that I'm explaining here. So maybe we can solve this. So here what it is telling like uh, if uh, yeah I have a matrix A and I can so I have to calculate this eigenvalues and eigenvectors, and then we'll see like we can diagonalize this matrix, or is there any transformation possible for this matrix where using similarity transformation where we can able to make this is diagonal. So to calculate eigenvalues, so again we will do this same thing which I was explaining here before. Like I have to basically construct a characteristic equation, and I have to set that to zero. I mean that is basically the characteristic equation. The determinant of this matrix setting to zero basically gives me a characteristic equation. So here also I have a matrix A, and I have to uh, get a matrix of this form, and then the determinant of this matrix F needs to be zero for the existence of non-trivial solution. So that if you do that, like you will see that like the determinant is basically so that is basically minus of I. So the eigenvalues for this matrix will be plus I, or one of the eigenvalue will be plus I, and the other eigenvalue will be minus I. So and one of other property of like like of these eigenvalues, like if you take the sum of these eigenvalues, uh, they basically uh, will give you the trace of that matrix. So if lambda 1 lambda 2 are the eigenvalues of this A matrix, then if I sum them up, like they will give the trace of this A matrix. So like you can see here, like if I uh, sum the diagonal elements minus I and I, that is 0. So here also I got my eigenvalues to be plus 1 and minus 1. So you add them, lambda 1 lambda 2, that is giving me 0, and also you add the diagonal elements of this matrix, that is also 0. So that is a uh, property of this eigenvalues. Basically they will come from some uh, I mean, if you take the general characteristic equation, they form a polynomial equation. So that polynomial equation basically gives these properties. This lambda one, lambda two is equal to trace of this, and also likewise you can. So lambda one, lambda two is your determinant of matrix. So these are some properties. Uh, yeah, but you got the eigenvalues, then you have to calculate eigenvectors. So eigenvectors you can calculate like first I can uh, yeah uh, that like let me say x is some eigenvector which has x1, x2 entries. So then I can write uh, a of x is lambda of x. So maybe, yeah, okay. So for lambda 1, I have, so I'm doing for lambda 1. So corresponding to lambda 1, there will be eigenvector that is x1. So A is times, um, let's say x1 has uh, x1 contains x1 and x2 entries, uh, the small x's, and I'm doing for lambda 1, so that lambda 1 is plus I, so that is I times x1 and x2. So yeah, so if you would solve this, uh, like this again forms a system of equation. So if you solve this, you will get like uh, 2x1 minus plus. So the first one is true. So here, so from here you can see if I can write. Maybe I can use the other eigenvalue solution. So I had two eigenvalues. So uh, one was I took I here lambda 1 to be I, and the other I can take that other eigenvalue which was minus I. So correspondingly I will have another eigenvalue, sorry, eigenvector. So that also I can do the same thing. This time I can write something x1 prime and x2 prime, and that is minus I x1 prime and x2 prime. So and using this, like you will see that like you will uh, sorry, wait a minute, here I wrote to x1. So, yeah, so the other vector, like you can calculate in the same way. um, so this one would be 2 x1 prime minus, sorry, plus I x2 prime equal to minus I x2 prime. So this term I can write this as uh, x1 prime equal to x2 prime, or I think this is minus x2 prime. So, or no, this is minus I x2 prime. Yeah, So here what happens like if these are your elements for this x2 vector, like I can write like uh, like x2 to be something of I times uh, x1, sorry, x2 prime is something uh, I times of x1 prime. So if I set like if I set x1 to be some value, like it can be any value, if I would set x1 to be 1, then my x2 to be x2 prime would be I. So this actually will give me uh, uh, this will actually give my x2 eigenvector or my second eigenvector corresponding to this lambda 2, that is whose first entry is 1 and the second is I, and like if I would have chosen any other value, like it would have followed the same relation of these entries. So it could be just a difference of some factor. So let's say a2. So like I can I can just call this x2 eigenvector to be something a2 1 I. Similarly, which I was doing here for x1, like I had x1 uh, 0 like from here, and x2 like I can say like I can uh, x2 again I can take it to be something let's say a 1, because if I would have chosen or if I would gone with any other like value of x2, this same x1 equals to 0 would have followed. So again, up to some factor, I can write this x1 some scalar some vector times this 0 1. So I have these two vectors. So yeah, now this forms a the eigenvectors for this given matrix. So you people able to like follow this, no? Hello, you people like are you like following this? Okay, like, Panas is able to follow others like okay, fine. So Anurag is also following it. So this is your like this is the way you calculate this eigenvalues and eigenvectors, and then there was a following a follow-up question to it. So the next thing was to see whether we can uh, uh, do a similarity transformation on this uh, A matrix such that it diagonalizes this A matrix. So in order to do that, one of the thing that we need to ensure that it should have a non-invertible matrix which is denoted here by T. So so as I was like telling you right here, so we are in diagonalization. We basically go from non-diagonal basis to diagonal basis. So in non-diagonal basis, uh, you can construct this T matrix, in this case or in this case, which is denoted here by P, by using uh, this non-diagonal basis. So what I mean, like I can take my T matrix uh, to be uh, x1 and x2. So these are my x1 and x2 like forms a basis for this vector space which I'm working on right now. Because why I can say this x1 and x2 can form a basis, uh, because like if you would check them, they would form a linearly independent vectors. this x1 and x2. So like if you uh, put the same arguments like as we were doing for so long, like to understand whether how vectors are linearly independent, you will see that eigenvectors from the like inherent definitions, they are always themselves will be linearly independent, and they can form a basis. So that basis, like using that, I can construct a matrix T, which I was telling you right there. Like in this part, like we basically want to go from this basis, which to a basis of this. So so that I can. So I have the first. Let's say the first matrix was 0 1. The second was 1. So these are the x1 and x2, which I'm using it for my T matrix. And let's say like the factors like which was there outside, maybe uh, what I can do is like I can write these factors, this x1 and x2. Like for this case, these are basically like normalization factors. So if you have gone through those lectures, like you have also seen like what are normalization factors. They are basically like factors which multiply to the vectors. So then when you take the norm, that will give you 1. So like for this, the normalization factor is simply a1 is 1, and for this, like the normalization factor is 1 over root 2. So finally, my x2 is basically 1 over root 2 1 I. Now, when you will take the normalization, that is x2 bigger x2, that will give me I, uh, or basically 1. I mean, so you have to also use this normalization factor in this, um, I mean, in your T matrix. So you can do that without using this normalization factors also. So just for like to make things complete, like I am using this because there is also a reason like upon using this factors, but let's not go to that right now. Maybe we can come to it later. So you can also do this, you can also write this T matrix without this normalization factors also. So then the next thing for our symmetry transformation. So uh, for symmetry transformation, we basically need our this we need to we are diagnosing matrix A, so which we are denoting by DA. So the diagonal matrix is actually given by T of A T inverse. So we got T right here. Then we need to calculate T inverse. So this is the symmetry transformation we are looking for. So once we got T, then we can easily calculate what is T inverse. So T inverse, like I hope like you know this uh, process of technique. I mean this process of uh, uh, taking the inverse of a matrix. So basically do this 1 hour of determinant, that is uh, and then you transpose and you write cofactor. So just you need to like take the inverse of this matrix T. Uh, so -1. This is 0. So then your T inverse is minus I 1 root 2 and 0. So then I got T and T inverse. Now I can uh, easily diagonalize them using this. Uh, so so the A matrix is minus I 0 to I. 0 to. So if you just do this metric multiplication, like you can just simply yield. Uh, so like if you compute this, then you will get this final result. So here you can see like we finally gone from like uh, one basis to the other, where we actually diagonalized this matrix A to DA. So here you can see this DA matrix. If you would calculate its eigenvalue, then you will again get I and uh, you get lambda 1 to be I and lambda 2 to be minus I for this DA matrix, because they are similar matrices, because they come from a similarity transformation. And whenever you have a diagonal matrix, you can like uh, f- from the very beginning you can always say that its diagonal entries are always going to be its eigenvalues. So that is what I have also written down here. This diagonal matrix basically are the eigenvalues of this similar matrices, this A or D or whatever, this A matrix, like which we are basically diagonalizing it. So its eigenvalues will basically form the diagonal entries of its diagonal matrix. So when you diagonalize it, the diagonal elements which this diagonal matrix will take are going to be the eigenvalues of this A matrix. So this is the way like you diagonalize. So uh, you need to have a non-singularity matrix. So here you see the determinant is non-zero. So the determinant is non-zero for this T matrix. So that's why we were able to calculate T inverse for it, and then there exists a similarity transformation which basically diagonalizes it. So this is the technique of diagonalization. So so are you people able to follow this?
Rosa,
Ah, yeah.
I'm not quite able to follow it because I think it's because you are
Mhm.
working with complex numbers, but when you work with real numbers, I think then it's easier.
Sorry, like I'm using complex numbers, but
Yeah.
then what happens?
No, I mean, sometimes it's actually hard to work with complex numbers than
Okay.
working with real numbers. So that's the
Uh,
problem I have.
so you're telling like I'm like working out of everything by taking complex numbers. If I do that instant with real numbers, then things would be easier. That is what you are trying to say.
Yes, sir, yes.
Oh, yeah. I mean, complex would be like they would be. I mean, they are more general, if you would say, like because
Okay.
complex numbers, when you deal with complex numbers, they would basically form a like a bigger vector space, a bigger set to start with. If you can work with those like in certain cases, like dealing with complex numbers will be a little difficult, but here what I was doing, like here I was just simply taking a like two by two matrices, and I just yeah, I took some this. diagonal entries to be some imaginary numbers. After all, this is a complex matrix, but it is not that really a very different thing if I would have started with real numbers also. In this case, it really doesn't. It really doesn't matter like whether I start with real or complex, but things should going to be remain same. So like you will find this like I mean when you have some like let's say bigger some I mean you work with some bigger matrices and its eigenvalues and eigenvectors may get little complicated as compared to the real ones, but otherwise like the idea the procedure like if you're following it then everything is going fine. So these things you need to understand like the steps that you go through and how you diagonalize a matrix and how you create a new basis out of a uh, old basis. So the similarity transformation is basically uh, like this is a transformation. This is a basis transformation. In other words, people like to call it because you go from one sort of basis to other. Like for example, if I have a like in Euclidean space, if I have a two-dimensional uh, uh, vector like this, with like if I call this as x and y, and if I do a similarity transformation, x and y forms a uh, set of bases for my this two-dimensional R2 vector space. So if I can do a symmetry transformation over this basis, it can uh, give me some other basis x prime and y prime, and you will see that like this is basically a rotation of this vector space or this rotation of this like if you can say this rotation of this my Cartesian system if you say in Euclidean space, like which we call it as x direction and y direction. When you rotate it by some theta, you get some new x prime and y prime uh, vectors. They basically form your basis for uh, corresponding to this orthogonal transformation. So the similarity transformations basically gives you an idea of transformation from one basis to the other. Like you initially had some uh, mm, basis, you started with some uh, x and y, and you end up with x prime y prime, where x and y and x prime y prime are your basis vectors. So like that is the idea of diagonalization or similarity transformations.
That makes sense.
Okay, but yeah, I got your point. Like complex numbers, like right now in this context, like which I showed you for this two by two matrix, like it's not going to be really hard in the sense like you can just work them out. Like
Yeah, it's why it actually is easy for the two by two.
yeah, right now like I've just taken very like simple cases to make you understand like how these things follows, like how the process for diagonalization and scenario transformations are carried through.
Okay, thank you, sir.
Okay, fine. So like any more doubts like if you have. Okay. So if not, then um, the other topic is on about this unitarity and orthogonal. So in vector spaces, like you come across like um, like in various sort of if I would talk about in language of matrices. So this unitarity and orthogonality they are actually defined in this way. So which I have shown here. So this U is actually uh, here are some metrics which is whose entries are complex. Like this is going to be uh, uh, your general case where you uh, take the transpose and it's I mean when you take the dagger of that complex matrix you basically transpose it, and then consequently you take the complex conjugate of it, and then when you uh, multiply with itself, then you get uh, identity matrix. And the same happens if you have a real uh, matrix, that is your matrix O with real entries, and when you transpose it and multiply with it itself, then you end up getting identity matrix. So this is your definition for unitarity and orthogonality. So if that is so, then you get U dagger to be U inverse and O dagger to be O inverse, or transpose to be O inverse. So when you have real matrices, then uh, your dagger would just simply means a transpose. So there is no point of taking complex conjugation. So, but in language of vector spaces, this unitarity basically preserves this mapping. So, what kind of mapping? Like when you take this inner product, so inner product of this u and w vectors, but when you see, like uh, when you actually operate this uh, a operator, you will see that the after operation of that operator, the inner product is going to be uh, is going to remain same, and this feature of preserving this inner product is actually like the uh, definitions that you generally come upon for unitarity and orthogonality on vector spaces. So where this UW some vectors on in your vector space. So that was the thing which I was telling. So if V is complex, if your vector space is complex, then you will always have unitary mapping. And if your V is real, then you will always have orthogonal mapping. So, a, so a quick question on this is um, so here the question is if this matrix A is given, is this an orthogonal matrix which you have to check, and the same you have to do with uh, B matrix which is unitary or not. So the uh, property which I just like showed you, that is the thing that you need to check here. So first, like for this A, so for part A, you can just simply check what this thing will give. Um, so I have signed theta. This is minus cos theta. So, and then you take its transpose. So, like if you check this, like you'll find your diagonal elements will give you sin square theta plus cos square theta terms. So that is basically one. So from here, like you can guess that like it is a orthogonal matrix A. So from for B also you can quickly check this for so this will, um, so if you do this multiplication, you'll find that it will give this kind of result. So which is basically not your identity matrix. So here from here you can say P doesn't forms a unitary matrix. So that is just a like a very simple check that you can do to check whether they are orthogonal or unitary. And so the second part was if you have a vector that is x, then uh, calculate this a is equals to a of a times x explicitly, as well as the norm x as the action of a on x conservates norm. So so what it is telling, like if you have some vector, and if you can calculate something using this uh, uh, uppercase A matrix, this capital A matrix, then so I can write this. uh, So basically, I'm just calculating which was given in the question. So that would give me so just operating this A matrix on this the web on this vector which was given in the question. So that uh, uh, gives me this final vector. So then that question basically asks like does the action of A so when I so the norm for this vector would be like you just take uh, this just take the inner product of with itself, or basically like you write x transpose x. So that actually um, um, so that gives 5. So so when you take uh, square root of this norm, so that will be your normalization factor. So your normalization factor is square root of this x transpose x, that is root 5. So root 5 was your norm, or I can write this to be a norm of the vectors. And when you operate this bigger a matrix on this vector, you came up with a different vector. So that vector was given as this sine theta. So that is what like I have written here. So so for you have to calculate norm for this vector as well. So again, you can do the same thing which I did it for x in order to calculate the norm. So you just take uh, A transpose of A, its square root will give you the norm. So if you just take the transpose and then do the matrix multiplication, you will get this, or maybe I shall write this. Let's do this: sine theta plus cos theta minus cos theta plus 2 sine theta. Uh, Take square root, that will give you, so this sine square theta sine, sine theta cos theta, and again we have cos square theta, then minus, so 2, uh, sorry, I'm doing some mistake here. So now, yeah, actually, this will be this A matrix which I have calculated here. I had a slide mistake. So this is sine theta plus 2 cos theta. So then now you can easily check, like you will get, so this is sine theta 2 cos theta cos theta. So now you will get this. If you do this matrix multiplication, you will get 5 sine square theta plus 5 cos square theta, then 4 sine theta cos theta, and again you will get the same term with the negative sign. So that is basically your root 5. So you see this, like when I did this operation with this bigger A matrix, that bigger A matrix was actually my orthogonal matrix that gave that actually that actually preserved this norm. So the norm, this preserving feature that I was telling earlier, like in the definition of orthogonality or unitarity, actually goes like this. So this was the uh, feature as reflected in this case, in this B part of the problem. So uh, and the same you can do for the last C part also. Here just the difference is, like you will you have to take this B matrix. So this B matrix, like maybe I can just quickly tell you, like this. So you have y1 to I, and now you are creating this B out of y by operating this bigger B. So that will, like that will give you 1 minus I 2 plus 2. So just you have to for the same steps back again, and yeah, 1 plus I. You can just check this later, like how it's one. So so this y vector which I'm taking here, which is given in the question. So if you take its norm, like you can take again with the same idea. So here instead of transpose, you have to take integer. So you have to, like do this thing. You have to take its transpose, and then you have to also complex conjugate it, and then all square root. So the complex conjugation will turn your I into minus I, and then you can just multiply, and you will get root 6. So but if you do with this p vector, uh, the same norm if you will take it, it will not be root 6, it will be something different, because this b matrix, this bigger b matrix, which we earlier found, that was not actually our uh, unitary matrix. It was not unitary, so you will not see this norm preserving feature in this case. So that was the idea of this question. So maybe like the time is already up, like it is 8 already. So maybe like I had one more small part to do, but maybe we can do that later next week. So so if you have any doubt, you can say are you able to follow this last part? It's fine. So and also Panas. So if you like people are fine with it, then like uh, good, then we can meet again next week. But if you have any questions, you can drop your doubts in this meeting, or you can just stop me whenever you feel you are having any doubt. Like, or you can also try to clarify any immediate doubt if you have in meanwhile during the week through this Google. I mean through this NPTEL uh, discussion forum. So which I mean I hope you can access that through your NPTEL portal. So there also I like remain active, and I actually uh, give replies. So like like today, like there are not many people only. I think there's two people here around. So you people are like following this course, no, or you are having any difficulties, or both of you like are you able to like follow this course very well, or like or any problem or anything any kind of issue? Okay, so then good then. Uh, I hope you are like following this lecture series, this NPTEL lecture. So this is a very important course. Like if you are planning to do a like if you are planning to do physics in future, this is really going to be important. And also in general, this forms a basic framework for all sorts of disciplines. So this will be a very important course. So just like understand it very properly. This is going to be vital for you. So okay, then we can meet again next time. So yeah, until then, see you.